Chapter 8, Single Slit Diffraction. The overview of the chapter is we want to compare the difference between interference and diffraction. We then go on to the diffraction intensity pattern. We define the diffraction parameter and then the number of minimas and maximas in a pattern, the locations of minimas and maximas, and finally the intensities of the secondary minimas, or maximas, excuse me. Lecture 8.1, Comparison between Interference and Diffraction. The bending of waves around obstacles is a fundamental behavior of all waves. Just as sound bends around a doorway, light waves also bend around corners too. And to show you this, I'm going to show you an applet, and this applet is the diffraction opening. And sharing my screen, here it is here. And so what you're seeing here is that these waves are coming into this opening. What you're finding here is that the waves are going to experience a slit opening. And as they experience a slit opening, what you're seeing here is that there is not the geometric shadow, but to the left and the right of the opening, that is a geometric shadow area. But one observes that there are interference and constructive and destructive interference in the geometric shadow area. So that means that waves have to bend around these edges of the opening. And another thing that you should note here is that central max, if you look at it, it's definitely brighter than the so-called secondaries. So let me go back to my screen. I just took a screenshot of that. And here it is. So when I look at this thing, here's what I'm seeing. Right here, this right here is the so-called slit opening. And this is the parameter they defined as A. So the slit opening is defined as A, and that is the parameter that defines diffraction. Another thing that you should note is that over here, you're having a geometric shadow area. So I would say that in the geometric shadow area, one observes constructive and destructive interference. For example, you can see that right here, and you can also see right here that that's a regions of constructive. On the other hand, you could see that regions here and also regions there, that's destructive. And the other thing that I mentioned here is that the central bright spot, that's right smack in the middle here, right? So if I was to show you what I mean by this, if I draw a line like this, I should have done this beforehand. You could see that everything to the left and right of those two lines is a geometric shadow. And the central line, or the central bright spot, is smack in the middle of this guy and is much brighter than the secondary maximas. So in interference, we call them, bright and dark fringes. That's not what we call them in diffraction. There is a subtle difference between interference and diffraction. Interference, okay, and this is a good way to define, interference and diffraction. Interference affects due to, here it is, combining not two waves, but many light waves is referred to diffraction. There is no fundamental distinction between interference and diffraction. In other words, one cannot separate out the two. You can't separate them. Now, to be a little bit more technical as to what is going on, what we find here is that when part of a wave is cut off by some obstacle, And what I mean by that, if we come back up to this image here, you could see that right here, you're seeing that the wave is coming in, but right here at that corner, part of the wave is being blocked. Right? It's encountering that obstacle and it's being cut off. So what happens here is that we observe diffraction effects that result from interference of the remaining parts of the wavefronts. And I think this is a more, ooh, that didn't come out very good. Let me try this again. This is a better way of thinking of diffraction as it hits an obstacle. So what I'm going to do here is to get a handle on diffraction I will summarize both interference and diffraction. Okay. So here we go. I'll start with the two-slit interference first. One, the most distinguishing feature or parameter of interference is the slit separation. Which we defined as little d. In Carlos's language, I essentially said it's the interference parameter. And you could see that the interference parameter, of course, is directly proportional to little d. So when I'm looking at this, in Carlos's language, this is the most distinguishing feature. So once again, this is Carlos's language. If you Google it, nobody's going to say this. And the reason why I call this the most distinguishing parameter, because it describes how much interference has occurred. And remember, this is directly proportional to the value of m. So if I, again, doing what we talked about before, if I look at d over lambda, and I start to look at what actually happens. So if this number is small, then that means I have few fringes. And if I have few fringes, then I'm going to say that this is a small interference. So the waves are not interfering as much. On the other hand, if this value is large, then I have numerous fringes. So therefore, this has a large interference because more waves overlapped. 2. We have a path difference equation. And when we look at the path difference equation, there are two equations that are intimately connected. I just said path difference, but there's the path difference versus the screen location of fringes. So in this case, we saw that the path difference equation was d sine of theta m. And what we know about the path difference, if we have MC lambda, or if we have MD plus 1/2 lambda, we knew that this was constructive. This is destructive. And just to be on the safe side, here, let me make sure that I have this. We called theta of m, this is the angular location of the fringe. But then what we're doing is that now we're looking at a linear distance. This is the screen location. And what we wrote here is that we wrote that y of m is equal to d tangent of theta m. So the reason why these are connected here is because theta of m occurs in both equations. Now, what this tells us here is that we find out that because of the screen location, what we find here is that the spacings between bright and dark fringes are equal. In other words, if I look at the screen location between the bright versus the screen location of the darks, those separations are exactly the same. So this is another fundamental difference between interference and you'll see diffraction. Then we started talking about the number of bright and dark fringes. So the number of bright, which we call MC, and dark fringes. So what we did in order to do this, we calculated a sequence of terms where m is 0 plus or minus 1 plus or minus 2, and we kept going on. So what we found here is that for constructive, we use the sequence for sine of theta was equal to lambda d times mc. And as we looked at the sequence, what we found here is that we started doing lambda d times, let's say, 0. And then we went to plus or minus lambda d times 1. And we just kept going on, and we keep going on until sine of theta is greater than 1. And then the sequence for MC ends. We did the same thing for destructive. So in destructive, we had a slightly different relationship that looked like MD plus 1/2. Then we followed the same sequence as with constructive with the slightly different equation. And then the other thing that we should look at here is that we dealt with the intensity function. And what we found here is that what we primarily dealt with was the relative intensity, which was equal to cosine squared of beta, where beta is equal to pi d lambda sine of theta, and beta was our phase factor. Now, if we plot this, here's what we found about the intensity. It was most useful to use the beta factor instead of something else, instead of like the angle or whatever. So if I look at this guy, let's say that this guy right here is going to be my relative intensity. So then I'm going to produce one interference maxima here, and I'm going to, let's say that I do this type of thing. So now let me copy this and I'll start my pattern. So the key thing with this pattern here is that all of the intensities have the same height. They all have the same value. And so when I look at this thing, this right here is I relative as a function of beta. And the way, the most useful way to identify where everything is at is we use this beta factor. So in other words, everywhere where I have constructive interference, I have whole integers. Oops, that's not really what I'm trying to say. I have values of pi. So positive pi, positive 2 pi, minus pi, minus 2 pi. All of these peaks. When I look at the minimas or the dark fringes, they occur in increments of odd 1/2 pi's. That's the most useful thing that's useful for identifying where we're at. And another important thing about this here is that this here is the maximum, and the max here is 1 or 100%. So what's key about this thing is this. All right fringes have the same maximum value or maximum height. Because these are normalized, this is, all of them have a height of 1. So now what I want to do here is that I now want to go in and look at single slit diffraction. So the setup for single slit diffraction is very similar to two slit. So when I look at this, I'm going to have a tiny opening, and then I'm going to have a screen at some distance, capital DOA. So what I'm seeing here is that there is this central line that we typically identify. Just like we did with interference. This guy is the screen, and clearly this guy right here, from here to here, this is what we call the slit opening A. And we also find that we have a separation between the slit and the screen. We label this as big D. So now, if I have interference, if I have waves that are coming in, then what I'm seeing here is that I'm seeing a series of waves coming towards the slits. So as they move in this direction, this is given, this light has a certain wavelength. So as the light interacts with the slit, as we saw with the applet, it produces a diffraction pattern. Now, before I get to the diffraction pattern, let's start looking at some of these features that are very similar to interference. 1, the most distinguishing feature or parameter of diffraction is the slit opening, which is defined as A. But in Carlos's language, it's the diffraction parameter, because the diffraction parameter is directly proportional to A, and this is defined as A over lambda. So when I look at this, once again, remember, this is Carlos's language. And as before, what it does here is it describes how much diffraction occurs. And guess what? This is also proportional to the m value. But I'm going to separate the language, and I'm going to call, instead of calling it m, I'm going to call it n, which is the number of minimas. So in the same feel as before, a over lambda then says that if I have a large diffraction parameter, that means I have many minimas. So that means I have I don't know, what language did I use before? I called it, I have a large diffraction. I don't think I like that. I'm gonna say it has lots of diffraction. On the other hand, if the number is small, then I have less minimas, and so therefore I have little diffraction. It has the same feel. So now we're really starting to see the difference here. There are two equations. So the path difference versus the minima locations. Now, here's what we find. Only the minimas can be calculated exactly. Whereas maximas are approximate. And really, I would say that for the first really three, there's an approximation, maybe even four. But after that, it's pretty much exact. So when I look at this, we really only focus on the minimas. So if I have destructive interference, then what I'm seeing here is that I get my path difference. And look what I'm going to define now. It's going to be A sine, instead of M, it's going to be N. Where for the moment, I'm going to define this as ND lambda, where ND this is the minima number of the minima, and it goes 1, 2, let me be careful here. It goes plus or minus 1, plus or minus 2, plus or minus 3, and on. Note, no zero value. So this is the path difference equation. And what we're going to see here, the screen location is going to be the same form. So the screen location of the minima is still given by d tan of theta n. Just as we talked about before, you can see here is that the angular location here and the angular location there are one and the same. They are connected. You can't separate them. So if I look at constructive interference, we have a different path difference equation, but this is a sine theta of n. This is roughly equal to nc plus 1/2 times lambda. Once again, where nc is now the maximum number, just as we did with fringes, and goes as plus, and this goes as plus or minus 1, plus or minus 2, like that. So it's the same type of thing here. So I'm going to have to say something about this. So this is not exact unless NC gets very large. It doesn't even have to be large. In fact, if by the time you get to 5, I would say that it's exact. It's about the number of sig figs. So there's a big difference between interference and diffraction. So it's common in interference to have the small angle approximation to be valid. However, this is not true for diffraction. It is not true for diffraction. So in other words, always assume no small angle approximation. So that means here is that two equations must be solved simultaneously. The two equations are a sine of theta equal to n d lambda and yn equal to big D tan of theta n. Originally, in interference, I was going to have you do this no matter what. But if you go online, people always talk about the small angle approximation. So I thought that was important to do it then. So now, here's what we find. Because of this here, it turns out that the spacings between minimas are exact. So if I look at the spacings between minimas, this is a constant and fixed value. They're the same separations. Okay, so I'm going to say that these guys are this implies here that the separations are the same. That is not true for maximas. So the spacing between these, but not true for maximas. So if I look at the spacings between maximas, these guys are not constant. They're not constant. And another thing here that we know here is that the separation between the central max, this is exactly equal to 2 times the separations of the minimas. It's always the case like that. So now let's talk about how we calculate the number of minimas. So if we look at this, let's look at 3 here. So now we have the number of minimas. This is ND, and maximas. This is NC, are determined by the sequence of sine of theta. But you're going to see here that I'm going to change it because I just wanted you to get a handle on it. But just to show you that the process is the same, is that if I look at destructive interference and diffraction, then that means here I have sine of theta n is then going to be lambda over a times nd. So then it starts to go plus or minus lambda a, and then I'm going to go 1. Then plus or minus lambda a, then I'm going to go 2, and you can see that the sequence now continues until sine of theta of n is greater than 1. Then it gives me the maximum value of nd. The same thing happens with constructive. I can then say that the sine of theta of n is going to be approximately nc plus 1/2 times lambda a. So then I start the whole sequence again until I reach that. And then finally, let's hit the intensity function. The relative intensity function reads like this. So the intensity of a single slit is equal to sine of alpha over alpha squared, where alpha is also a phase factor that now reads pi a lambda sine of theta. Look how similar this is. It's very, very similar to that of interference. But it's definitely more mathematically rich, as we'll see here. So now, what is the pattern look like? So if I look at the pattern, it's going to look something like this here. So what we're plotting here is we're plotting I relative of alpha. And so what we're going to see here is that in this situation, we're going to have a very broad central max. And then what happens is that these guys get smaller really fast. So if I look at this, you're seeing here is that right in here, you see here is that this guy here is a broad central max. And then these other ones, these smaller ones, which are much smaller, these are called secondary maximas. And what you're finding here is that we can label these with the value of n. So note that they're symmetric to the left, but I'm not going, maybe I should do that, just for the sake of, just for the numbering issues. So now if I start to look at that, this is the value of n. So if I look at this, there's no zero value. Now, if you want the minimas read 1, 2, 3, 4. -1, -2, -3, -4. I should have written these a little bit lower. Right, so there's no 1, so this is -1, 1, 2, 3, 4, -2, -3, -4. So these are the n values. Alpha is the phase factor. And here's what the phase factor tells us here. It tells us that this guy does have a 0 for the phase factor. At 0, it's a maximum. But if you look at the sign of alpha, anytime sign of alpha has a function of pi, it's 0. So wherever sign of alpha is 0, then it's 0. And it turns out that every factor of pi, we get zeros. So if I now set up a table to just try to summarize all this information, I'm then going to say that here's a summary of both interference and diffraction. So this is going to be a big table. So the first thing I'm going to do is I'm going to just start writing out. Okay. I want to talk about fringes or maxima or minimas. I think I'm going to call this numbers, the fringe number or the minimum. Then so when I look at this, I'm going to come down and I'm going to, nope. And then I'm going to look at the path difference equation. And then I'm going to look at the phase factor. And then I'm going to look at the relative intensity. So here I go. So the first thing I'm going to look at, I'm going to try to break this. Okay, now I know how to set it up. So this is a pretty comprehensive table of all of the details. So I'm going to color these to separate them. Actually, I think I'm going to do this in blue. So everywhere where we see blue, we're going to talk about interference. And we separate constructive from destructive. So then if I do this, everything in blue here is going to be interference, as I've already stated here. So let's go put this together here. So here we go. MC, that has 0, plus or minus 1, plus or minus 2. It goes like this. MD has the exact same values. When I look at the path difference equation, it reads D, it's going to read D sine of theta of M, and this will then be MC lambda, and this will be MD plus 1/2 lambda. So if I look at my phase factor is beta. That reads beta is then going to be pi d lambda sine of theta m, and then our relative intensity is cosine of beta like this. So now, if I go to diffraction, I want to separate diffraction from interference. But remember what I said here, they're very closely connected. I really cannot separate the two. And so we would expect that there's going to be subtle differences between these guys. And here we go. We have diffraction. And in diffraction, we have destructive, maybe I should say constructive, and destructive. So when I look at so instead of calling it M to separate it, I'm going to call this N. I got to be careful here. NC is approximately equal to plus or minus 1, plus or minus 2. That's not true for ND. It's exact. And the big separation here is you could see that one is approximate and there's no zero in diffraction. So then I have my path difference equation, and we gotta be careful how we write this, because this is equal to, this is approximately to NC plus 1/2 lambda, and this guy is exact at ND lambda. So you can see that they reverse between interference and diffraction. The phase factor is almost identical with the exception of A. And then we have a more complicated relative intensity function, which we'll get to later on.